enough about eyeglasses and jobs. Course-wise, you all know the first part that was on last week, that we're a little slow, and I'll try to figure that out. If you haven't done the mid-course survey, please go do that. I would really appreciate it. Midterm grading is going great. I'm sure we're going to get it for you Friday-ish, and if not Friday, Saturday. Homework 5. So there's some confusion, my fault. Homework 5 got released late, and when it did get released, it accidentally had the original due date on it. It is due Sunday night, Sunday, February 14th. That is when the grade scope will close. So you guys lost the weekend for doing it last weekend, so you're getting the weekend this weekend. Homework 6 is going to release at the normal time, and homework 6, we will be back on our regular Friday turn-in schedule, okay? So next week is President's Day. Monday is a no lecture day. I may very well release another couple of demo videos, videos that show you some more scikit-learn kind of stuff. I'm going to actually try to do that this week, but I have no idea where I'm going to find the time. So if I don't get it done this week, there's definitely going to be a couple of President's Day demo videos dropping. Okay. Another big thing is that it is time for you to think about your final projects. Okay. If people have not seen, should have brought this up a minute ago. Bring this to the right window. Okay. Of course, I got stuck by accidentally dropping it on the wrong place. Okay, let's do it the Jason is not a Zoom moron way. There we go. Okay, so if you all haven't seen, there is on Canvas this final project description. So please take a look at that. We only have a month, okay? And I can tell you that the final project is going to take you more than a week to do, okay? Those of you that are waiting for the week before finals to do this, you're going to find yourself in trouble, especially because you know you're going to be slammed with other classes that have final exams and stuff like that then, okay? So start working on it now. And the first thing you can do to start working on it is to read our prototype paper, the Caruana paper from 2006. All right, this paper is a comparison of a bunch of different machine learning algorithms. So they're all taking on a bunch of different binary classification tasks and seeing across a bunch of different classification tasks, are there some algorithms that are better than others? Okay, that's what you're going to be doing. So just as soon as you can, start reading the Caruana paper. It's not the easiest read. So, you're going to want to take some time with it. Come to, discussion section in office hours, ask some questions about it. And once you get both the concept of what they're doing and you start to understand the bits and pieces technically, all right, then we can go into details about how you're going to do this. And that's where the rest of this big, long spiel is going to come in. All right. Reminder, when you guys do a report, you can either do this as individuals, in which case you're just going to follow Caruana for a bit and basically do a subset of what the Caruana paper is. If you're doing, for those of you that wish to investigate doing a group project, you're going to have to do a lot more. And, basically, if you have 3 times as many people, I expect 3 times as much effort. And I expect you to come up with some ideas above and beyond what's in the Caruana paper. So that's just a précis. We're going to talk more about this several times over the next week or two, okay? Critically, I need to get us through a course on using cross-validation, on a lecture on using cross-validation for feature selection and model selection and hyperparameter tuning. So we need to get that lecture under our belt, which should come next week. And then we can really go into the details of the final project after we've had that lecture. Okay? So, any questions? Because they're
quick question. Where is the link for the mid-course survey? I can't find it on Canvas.
It should be right there in the modules. So week 6, right here.
Oh, for the mid-course survey.
Oh, mid-course survey. I'm sorry. Did I not post that somewhere? All right, I'll post that somewhere. It's in the PDFs. So Monday's PDFs has it for a starter. Okay, as does this PDF.
Okay, thank you.
There we go. All right. Boo-doo-boo-ba-doo. Hey, where'd my presentation go? See, now I need new glasses, Shay. Can't find my presentations. Okay, let's try it this way. Oh, okay. Decided to shift the window. Keynote, bang, bang. All right, we're here. Now for some real fun, because support vector machines is the first thing that really makes everybody go, math. Okay. So before you freak out about the math, the great thing about support vector machines is, well, 2 things. One is they're incredibly powerful, very useful. If you only have 2 machine learning algorithms that you're going to try on something, one of them is going to be a support vector machine. Okay. The other second great thing about them is that intuitively, they're very easy to understand. It's just the math that's a problem. Okay. So let's start with intuition. We've got a classification problem. All right. I invite anybody that wants to annotate my screen right now. Can anybody draw a good decision boundary on this? There we go, Maxwell. All right. We've got some votes in here. I want to see a bunch. I want to see where the main ideas lie, and feel free to contradict your classmates. The ideal, I would have had you all like blind to each other so you couldn't see. All right, we've got some people who think their own way here. Great. Okay, now that we're getting some density, oh, I like some people giving me the funny versions. So, all right, if you look at the density of the results here, you may see the beginnings of an agreement about what makes a good classifier, okay? If you were going to intuitively try to state what makes a good classifier here, what could you kind of postulate as, like, you know, a 1-sentence version of what makes for a good classifier? Anybody? Chat welcome too, if you want to do it that way. All right, consistency is the 1 vote that I'm seeing on the chat. All right, so that's a good criteria. But even more, I want to know, oh, we got a robustness. Oh, look at that. People are getting creative. All right. So let's take a look at a couple of the lines we've been seeing drawn here. I think this is Richard's line. Hey, dang it. I think this is Richard's line right here. Okay. So this line, do you think this is a robust classifier, one that's going to be consistent with lots of different versions of this data? I'm going to argue probably not, right? So if you bring in like, maybe some more noisy data points, maybe you get something over here, right? Okay. So, all right. So maybe you don't want something that does such a close shave. So if you don't want it to close shave one of these groups of data points, maybe you want it kind of in the middle between them, right? That's our problem. If we want to formulate the idea that something that is maximally robust is going to, generalize well to new examples of this data plus some more noise, then maybe what we need is something like this. Okay, so we've said, close shaves like, oops, I can't draw. Close shaves like this are a bad idea, right? But maybe what's robust is something that kind of lies in the middle. Okay. So let's draw some new data here, right? And you can see that, if we have something in blue here, it will classify correctly these new data points that I threw up on the screen, all right? Whereas the two ones that are close shaves to one of the sets of data are a bad idea. And that's where we get this idea that we want a classifier that's going to put its boundary right in the middle at the midpoint between two data sets, sorry. So if we have two data sets, how can we define the midpoint? Well, what support vector machines do is they find support vectors. What is a support vector? Well, so the support vector is just those points on the two classes that are closest to each other. All right. Here's a support vector, and here's a support vector. These two data points are the closest to each other of any of them, except for the ones that I just threw up, right? So maybe we would say, maybe this is a support vector, maybe this is a support vector too. Maybe these are all the four most close to each other across the gap between the two. All right. So the way we're going to formalize the idea of a support vector machine is we need to find these close data points, and we need to figure out how to place our division, our boundary, in the middle between those points. Okay, so I'm going to kind of erase that line and redraw it a little bit better now that we have our support vectors. Not the eraser. I need the drawing tool. Thank you very much. Okay, so the idea is that these distances, if I could draw better, should be equal. Okay, we're going to pick our weight vector such that it is lying at an angle inside the situation such that these are all the same distance apart. Okay. Okay, so it's a two-step process. We find our support vectors, we find those data points which are closest to each other across the gap between the two classes. And then we find the line that bisects that gap, that has an equal distance on each side. okay? Notice what's awesome about this technique. We only have to find these couple of support vectors. We don't care anything about all the stuff out here, okay? This stuff out here, it's all just noise. It can move around and it's not going to affect our answer. So this is one of the reasons why support vector machines are really, really robust, because the only thing they're going to use to make their decision points are the data close to each other across the gap between the two classes. So if this data point here moves by a little bit over to here, it's not going to affect the solution in any way, shape, or form. It would for any other kind of classifier we've talked about so far. So we have a kind of robustness built in. And we also have this notion of finding the thing that bisects the two classes perfectly with a gap of equal size at either side. There's one last detail that I haven't added to the picture. And that is the idea that we want to maximize this distance in here. We don't just want to be perfectly bisecting. We want to push those distances as far apart as we possibly can. So when doing that, we can make ourselves more robust, right? If we have a little bit of noise and we get a new data point, right? And this new data point is, maybe a little further away. If the distance in here is big, then that new data point is still going to lie on the correct side of the line. But if the distance in here is small, then the same amount of noise could push our positive class onto the wrong side of the line, okay? So we want to avoid that. So we want to push that margin, because we call this thing in here the margin. The distance, oh God, I'm sorry, I shouldn't use the same colors. Let's do something bright. Let's do some green, okay? The distance between these two sets of points defined by those support vectors, that is called the margin. And we want this margin to get big, okay? We want to push things apart. We want to put our dividing line, our boundary, right in the middle between the two sides. So right in the middle of the margin. Okay. Does anybody have any conceptual questions about support vector machines? Is it clear what we're trying to accomplish? Does anybody want to add a doodle before I go off this page?
I guess so. Basically, you're just, because of the fault that a decision boundary could have, you're trying to instead, through support vectors, create like a decision box. Is that a good way to think about it?
So we still have the same linear decision boundary, okay? But now we care about two new lines, right? So, and this is what's forming your box that you're talking about. We care about this line here that goes through the positive class support vectors. And we care about this line here that goes through the negative class support vectors. And we also have still our original decision boundary, which I'm now going to redraw in orange here to make life really ugly, okay, right in the middle, okay? So we now have three lines rather than a box. We have our decision boundary, and we have our positive margin. I'm not going to use orange, I'm sorry. Our positive margin and our negative margin. Good?
I see. Yeah.
Okay.
I missed the piece where you said how the support vectors are actually kind of decided. Is it like a line that's drawn between like 2 points that are closest to the other class? I missed that piece.
Yeah, so exactly. So I haven't gone into the formal definition yet, but yes, the data points from the positive side that are closest to the negative class, and the data points on the negative class that are closest to the positive class, those are your support vectors.
And is it exclusively 2 data points and that vector is drawn within the 2 of them, or?
You don't need to do that, no. So you can calculate it on just a couple of support vectors. It doesn't have to be 2 on each side. But the important part that you do need is you do need 2 on at least one side, okay? So that gives you the orientation of the line. So you do need to have 2 on one side, but you could have just 1 on the other, and that would be fine.
All right, thank you.
All right. So let us, clear this crap out of the way. So let's talk about the margins. So we know what's happening right here, right? And now I get to switch over to my iPad so I can actually draw well, okay? So we're totally used to the decision boundary, right? The decision boundary is just Wx plus b equals 0, right? That's definitional. So how are we going to define the positive margin and the negative margin? Well, it's actually Wx plus b equals +1 and Wx plus b equals -1 on the negative side, okay? So these are definitional, right? What we're saying is the margin is 1 unit away from the decision boundary. Well, 1 unit of what? Right? It's 1 unit of size of the weight vector. Okay? So let's take a look at the math here. We have the negative decision boundary right here. Okay? Wx on the minus side plus b equals -1. All right? This is the equation for the negative boundary. Right? We have the equation for the positive boundary, right? So this guy is right here. Okay, well, to go from here to here is we just have to take the negative boundary and add in the size of W. Well, the size of W multiplied by a constant, all right? So the margin is really defined as the 2 norm of the distance between these 2 margin lines, all right? So the total margin distance, this thing in here, margin M, that is just the 2 norm of the one margin subtracting the other one, all right? And it turns out that you can formulate that such that we just have a constant lambda, and we can solve for what that lambda is, okay? So there's my terrible animations that I've already drawn over. So it turns out that lambda is 2 over the magnitude of the weight vector. Okay, so this is the same as that, right? So this is the slide is saying it in a slightly different way, right? So just to make ultra clear, this is the L2 norm squared, okay? So W transpose times itself, or in other words, the dot product of W on itself, right, is the squared L2 norm. Or we can write it this way, right? That the L2 norm is the square root of W transpose W. Same difference. Okay. So you can see right away that putting in these values in here, right? So if 2W transpose W is the lambda component, and we know that the magnitude of W itself is this. So now we can clearly, cancel out things, right? This goes away and takes away a half of that down there. And that leaves us, this formulation. So the size of the margin is got the magnitude of the weights in the denominator. The bigger the weight vector is, what happens to the margin? Bueller? That's right. Exactly. It grows. So the magnitude of the margin gets smaller as the weights get bigger, and as the weights get smaller, the margin grows. So I've seen the question in the chat and I'm about to answer it, right? So the two, we're going to actually show you the derivation in a minute, but fundamentally there's two distances in here, right? There's the distance on the one side and the distance on the other side of the boundary, and it comes from that. So let's get right to answering that question about where does that 2 come from. Okay. So we start with the same setup as before, right? And we know that what we're after is the margin is the distance between these two lines, the positive side and the negative side. Okay. We know that that's lambda times W. Okay. So let's multiply things through. All right. So here is, right, we're going to put in W transpose times the stuff inside. We're going to take this stuff here, right? W transpose X plus B, all right? And we're going to try to write what would happen at the positive side by adding in the plus lambda W that would get us from here up to here, okay? So multiply it out. And we know that if we have, again, the W transpose X equal to -1 here, we add those two together and things start to drop away, right? So +1, hold on, how did this work? This needs to be a negative, doesn't it? That's why. Right? +1 minus a -1 yields +2. Okay. B minus B goes away. This goes away. And we're left with this, which is what comes down here on this side. Okay, so the problem there is that that was supposed to be a minus. So we just did a coordinate transform, right? We started off by replacing the positive side with the negative side plus the thing that's going to shift us up there. And we get down to this form on the bottom. which can be simplified. Whoops. My bad. Sorry, people. Which one is that? I guess it's that one. Yep, that's where we were at. Okay, get my notes back. I apologize for the slide mistakes. Okay, so this, right? Remember that this and this are equivalent notation. And so that's where we get. Okay. And again, so this is the derivation of that whole thing. But remember that fundamentally, where did that 2 come from? That 2 came from this operation right here, right? The 2 happens because there's 2 sides here, right? And each one of them is magnitude of the normal vector, right? Sorry for having to write super tiny, but does that make sense to people? I mean, I know the math is hairy, but conceptually, just understand that the magnitude of the weight vector is 1/2 of the margin. It is the distance between the decision boundary and the positive side is the magnitude of the weight vector. And likewise, of course, also between the decision boundary and the negative margin. Okay? And the crazy, crazy thing about all this is that what we're doing is if we want that margin to get bigger, we need the magnitude of the weights to get smaller. When we previously had a situation where what we were doing was minimizing the magnitude of the weights, what did we call that? Yeah, I called it squeezing the weights, but there's a terminology word I want, Oscar. Regularization, says the real Jason Fleischer. Somebody has got some game on the Zoom names. Probably was Fernando Tatis Jr. too. So yes, regularization. When you squeeze the magnitude of the weights, we're regularizing. And we know that regularization helps us avoid overfitting. Oh, Fernando Tatis Jr. is still here. Oh man, too many people have got the game. All right. So yeah, regularization. That is what we are doing. By maximizing the margin, we're also regularizing. We're preventing overfitting, right? And you can kind of see that intuitively. When we can force big separation between the positive class and the negative class, we're unlikely to make mistakes, right? New crazy noise data is not going to cross a large margin. It would cross a tiny margin, right? Quite easily. So intuitions are really clear in SVMs. Do the margins have to be parallel? Yes. The margins definitionally are the same WX plus Bs, right? Like exactly what happens in answer to your earlier question, Chase, was that, we have the decision boundary, which is n equal to 0. We have the positive margin, which is the same equation equal to 1. And we have the negative margin, which is same equation equal to -1. And that is why definitionally, this is the distance is the magnitude of the weights. Why is there a blue dot on the other side? Oh, what if there's a blue dot on the other side? Great foreshadowing. We're going to get into that next. What if we don't have separable data, right? That is the question at hand in the chat. And that is a great question. We would like to figure out that problem for sure. So, before we get there, we've got one other thing, which is just to quiz you guys. How can we maximize the margin, right? What would W look like if we wanted to increase the margin? I've given this away already, but any votes for A, B, and C? In the chat, on your voice, draw something on my screen. Exactly. The chat room knows what's up already. We want B. Yep. Infinitely small magnitudes, right? We want tiny weights. We want it fully regularized to maximize that margin. All right. So all right, let's get to the good question that we were just asking. Actually, never mind. We've got one more stop along the way. So we want to show you what would this loss function look like before we get to dealing with slack variables and when we have non-separable stuff. All right, so we want to minimize that margin, right? And we have a training set. And we know that what we want to do is minimize that margin, but we also want to minimize misclassifications at the same time, right? It's no good making my margin huge if it has nothing to do with the data, okay? So we want to maximize the margin while also minimizing misclassifications. Okay, so we can do that. We can minimize the size of the weight vector, and we can also minimize misclassifications, which is what's going on there. All right. So in this case, we know that, yeah, so we've already got this part, right? There's what we're going to deal with. All right. So how does this look like? Our loss function is going to be the hinge loss. And if you remember earlier, I was calling this the hinge loss at the perceptron, right? That's the perceptron algorithm. Okay, it's got the same form, but there's a critical difference. Perceptron was at 0 that it started the hinging, okay? This one, it is at 1 that we start the hinging. So what is that? Why do we start coming up off of the 0 error at 1? Well, what if we have a data point which is between the positive margin and the decision boundary? Well, our goal is to maximize the margins, right? We want the line between the two closest data points. This would become a new support vector, right? And that new support vector is too close to the decision boundary. So we want to penalize that. Anytime we get something like this red data point, which is a positive class, and it's on the right side of the decision boundary, dude, right? I mean, it's not going to be misclassified, but it's too close to the decision boundary. It's inside the margin. So we want to penalize that. So that data point falls over here, okay? It is something we want to penalize. We want to say, don't let that live there, okay? But we don't want to penalize it as strongly as something which is truly a misclassification, okay? All right, so like this, here is a misclassification. It's a blue dot, which is on the wrong side of the decision boundary and even on the wrong side of the margin. Okay. So that one is going to live over here on this point. We're going to get a much higher overall loss for that. Okay. So originally we had our correctly classified but inside the margin, and we had our incorrectly classified wrong side of the margin setups. All right. So critically, what you need to see here is that this is where this one comes from. Is that cool? Everybody kind of understand that idea? So, okay, now Yun-Chun and everybody else probably want to know why it's subject to y times the WXB minus 1. Okay, so this part minus 1 is this, right? What is the y sub I part? Well, remember that clever trick we did during logistic regression where we don't care what class something is? Okay. So if we're dealing with a positive class situation like this one over here, y sub I is going to be a 1, right? Which changes nothing. Okay. So that is the math like we've been doing it. But what about in the case where we have this one? Okay, that's a negative class. So it's going to be a minus 1. So it's going to throw a negative sign on the front of stuff. Okay, and that means that we are going to immediately be operating off of this margin, right? That minus 1 goes through, and we're operating off of the other margin, and that's why this one ends up way over here, far away from that setup in the negative zone. Okay, so this is the same trick we saw with the log loss, where multiplying by the true target value enables you to use one equation to represent both the positive class situation and the negative class situation. Cool, at least conceptually, even if you're going to have to dig through the math again later, you at least know what the math is trying to accomplish? Or do we have questions? Anya asks, can WX have large negative values that when multiplied with minus 1 will still be positive? Large negative values. So
I could just speak.
Yeah, go ahead.
If that's easier. Yeah, so like what you see, it's like the whole thing was that when you multiply yi when it's negative into here and then subtract it by 1, it'll be it'll bring it to be negative, right? But then what if WTX, the values within that are like large and negative? So when multiplied by -1, they'll be positive. I mean, it's an edge case, it's a reach. So just tell me if it's not worth paying attention to.
I'm not sure if I've figured it out yet, because what's going to happen is that naturally, of course, can occur when your X values, like, when the W values or the X values allow that. But those will be in situations where, I mean, fundamentally, you are in a case where, yeah, I guess maybe I'm just not quite getting it. So
it's okay. Honestly, it's probably not that important anyway. So.
Okay. All right. Well, if I figure out the question and figure out a good answer, we can chat more about it later. Okay. All right. So critically, again, the hinge loss is, going to define this thing here is going to give this line, okay? If you let that go on, maybe this is where you're talking about, Anya, where you're going to get large negative values, right? We want to chop that off. We don't want that line to continue on. So what we do is we implement the max of 0 and the hinge, okay? So anytime the hinge gets to be a negative y value, right, then we chop it off and we just flatline it at 0. And that's what makes the hinge, okay? You saw the same math during the perceptron learning function, right? So there's our hinge. Our hinge is going to penalize things. It's going to penalize strongly things that are just completely wrong, like this one. It's going to penalize in a more weak fashion things that are on the right side of the decision boundary, but the wrong side of the margin, okay? And that all goes in here, right? Oh, one bit of notation to recognize. This stuff, the maximum function, we are going to notate it like this. So we can, instead of writing max everywhere, we can just write that positive sign. Only the positive end of this function is how you would want to interpret that bit of notation. And otherwise chop it at 0. Okay, so here is the hinge. And remember, the hinge is it's a misclassification error, all right? It's a misclassification error plus this stuff in here, which is going to penalize things that are correctly classified, but on the wrong side of the margin. All right, and the second part of the loss function is the margin, maximizing the margin by minimizing the weight vector. Okay, so we want to do both things, but what if they conflict, right? Well, this magic parameter C tells us which one to care about more, right? When C is a large value, we care much more about the misclassification. This is called a hard margin classifier, right? It's going to care about the misclassification. It's going to draw the margin wherever it needs to, okay? If the C value is small, then correspondingly, we're going to care more about the weight vector, right? And the weight vector is going to make the margin as big as possible. And that's called a soft margin classifier. Okay. So, all right, let's do this with the non-separable data, the question from 20 minutes ago that I just now got to, right? What if we have things where we have these data points that are on the wrong end of stuff? There's no way to deal with them. We're going to introduce this slack variable, okay? We're going to allow some slack in the system. We're going to let things go on the wrong side of the margins. And we're going to let them go by epsilon, by this, actually, I guess this is supposed to be psi. So this Greek letter psi represents the amount of slack in our system. So what is the amount of slack? It is how much you would have to move those data points by in order to get them on the correct side of the margins, all right? Not of the decision boundary. We need them to move all the way onto the correct side of the margins, right? Because that's what our hinge loss tells us we care about, all right? So we are going to use this slack variable, which now is going to be defined this way, right? And we're going to put that on the right side of the equation and use that for our function. Okay? So anytime we have slacks that are bigger than 0, they're going to contribute to this. Okay? So it's the same idea, but we just allow a certain amount of slack, and we can account for that in the C variable again. When the C variable is very, very high, we don't allow much slack. When the C variable is low, we allow a lot more slack. So we have the same format, really. You haven't really changed the equation. It's just that we can formulate the idea of what it's doing to realize that by making C a low value, we let slack happen and we can deal with non-separable data. So what's going to happen in this case is that the support vector machine is not going to actually pick support vectors that are fully separable. It's going to pick support vectors that are convenient, right? That exclude most of the mistakes, but not all of the mistakes. All right. So we know our math at this point. We're just past time. So I just want to note that we are going to solve this problem with gradient descent. Right? And we know what the gradients are here, right? At this point, the gradient is 0. So if our value, whatever data point it is, if it's a positive class, there's a +1 here, right? So this becomes the positive margin. This equation becomes the positive side of the margin, right? So if we are anywhere over here, we're on that side, and our gradient is 0. Okay. If we're a positive class and we're anywhere over on this side of the world, well, we're operating in this regime then, and we figure out how bad we are, right? But it doesn't matter because our gradient is always a constant here, right? So our gradient is always just the constant, which is our xi, okay? yi times xi, and our yi is determined by which side we should actually be on. Okay, super simple. The gradient is just one constant value whenever we're on the wrong side of the margin. Otherwise, it's 0. Okay. So the last thing, if we're going to do gradient descent, we need to know, is this a convex function? Do we expect to get the right answer doing gradient descent? Does anybody know if this is a convex function? And can you tell us why? Nobody?
Could I try?
Yeah, go for it.
Is it maybe convex because we have the weight square?
Mm-hmm.
Okay.
Parabolic, exactly. So this is a convex function in the weights. You're absolutely right. Okay, what about the right-hand side? The hinge loss. I mean, you can just look at the shape of the hinge loss. Can you tell me if it's convex? Yep. Okay. So is a convex function plus a convex function a convex function?
Yeah. Yeah.
Yes, it is. Yep. Add two convex functions together, they will also be convex. So we know that this whole ugly mess is a convex function. We know that gradient descent can theoretically get us to the global minima, provided we pick the right step size. Okay? You did it. In 55 minutes, I think we covered the basics of one of the most scary bits of mathematics we will encounter this quarter. So I'm sure there's going to be more questions on this next time, and we are going to cover more about support vector machines. But this is it, people. You've already passed the peak of the class. So congratulations. So you're all welcome to hang out, ask a couple more questions, but anybody that needs to, of course, I thank you very much for your attendance.
Thank you.
Could I ask a question about the hinge loss and how different parts of it contribute to the shape? I think
Yeah.
it's the slide before non-separable data. So you mentioned about where the different where the different red and blue points would fall. I think I might be just like slow at taking notes or something, but could you like re-explain the shape of the hinge loss and why those points
Sure.
fall there?
Okay. So, oh man, I'm sorry. Let me, as bad as it's going to be to draw with the mouse, let's do it with the mouse so we can get rid of those. Okay, so this whole function, right? The y sub I is about which margin you're on, okay? So y sub I is going to be +1 when we're talking about a positive class, and it's going to be -1 when we're talking about negative class, okay? So when that's a +1, this is going to be that equation. And when this -1 comes through, it's going to be that equation, right?
Mm-hmm.
Okay, so this equation can operate on either side, on either margin, according to that +1 or -1. Okay.
Mm-hmm.
All right. So in that sense, what we're doing is we're just, operating on, are we more than one away from the decision boundary, where one unit is defined as the magnitude of the weight vector. Okay, so anytime we are more than one unit away, okay, so let's just talk about just the positive class case here, but the same thing applies to the negative class case. Just operate on the other boundary, operate on the other margin, okay? If we have data points that are over here that are positive class, well, they don't affect our classifier. We don't care about them. We don't need to adjust our decision boundary. We don't need to adjust our support vectors, all right? So anything that's more than one away is going to fall over here and generate no loss, okay? Anything like this new big red dot that's here in the animation that is inside the margin, okay? It's a new positive class data point that's closer to the negative class than the positive margin that was defined by, assumedly, this is the support vector on the positive side, right? It's the thing that's closest to the negative side, right? So if that's the case, then this is a bad thing because now this would become the support vector. So it's closer. So that's a loss. All right. We have to adjust our weights so that we are, now that this is the new support vector, we need to redraw stuff, you know, so the boundary is somewhere in here. Okay.
Mhm.
So to do that, we need a penalty. So this one is going to fall in this regime here. Okay. It's within the decision boundary. It's on the correct side of the decision boundary, right? This is the decision boundary right here. Okay.
Mhm.
But we need to penalize it because we need to adjust the weights so that this becomes our new support vector. Is that clear?
So you said that the the vertical line is the decision boundary?
Yeah, this is right here is, you know, Wx plus B equals 0. Is it right at this point?
But then I think you mentioned that the red point would fall like on the on the place where it says 1. Would it not fall there?
No, so the red point
Oh.
here. So the red point is where it's drawn right now.
Mhm.
Originally came from right here.
Yeah.
Hey, right, this color. Why is that what red looks like on the screen now? Whatever. Okay. So it's on the correct side of the decision boundary, right? This is the decision boundary, right?
Mhm.
The black line. So it's correctly classified, but it's inside the margin, right? This is the margin. This point here represents this line here, the +1 margin, one away from the decision boundary.
I get confused how a point represents a line. Maybe I just get confused by the
Remember, the decision boundary is Wx plus B equals 0, right?
Yeah.
We have 3 lines. This is the decision boundary. This is the positive margin. And this is the negative margin. And the positive margin is one magnitude, actually 1 square root of magnitude away from the decision boundary. And the negative margin is 1 square root of weight vector magnitude away on the opposite direction, right? So definitionally, the decision boundary is at 0. The positive margin is at +1, and it's +1 weight magnitude, right? And the negative boundary is at -1 weight magnitude. This is the trick.
I think I might need to come to office hours or something about this.
Yeah.
I want to let other people ask questions, but thank you.
Yeah. So just to make super clear, okay, if we had a negative class point that was in the same situation as the positive class point, it's on the correct side of the decision boundary, right? It's on the negative side, but it's not over the margin. That point is going to fall in the same location here, right? Remember, this representation here of the hinge loss is agnostic to whether we're talking about the positive or the negative margin. Which one we're talking about is determined by that.
So whatever is on the diagonal is something that like represents the points that are on the correct side of the
Yeah, Everything here
Mhm.
is something that's where we've just drawn it. It's something that is correctly classified, but
Mhm.
on the wrong side of the margin. Everything that is over here, or over here, or over here, or over here is
Mhm.
something that is correctly classified and on the correct side of the margin, and we don't care about it, and we have zero loss. Anything which is, oh, new color, we use light blue. Anything which is over here is something which is horribly misclassified, okay? So it is a negative point over here or a positive point over here, right? It's misclassified and badly so, because it's well over the margin, even on the other side, okay?
So where the 2 points, the pink and the blue points are drawn, that is not like on the horizontal zero loss.
Correct. Remember what these points in here are, they are
Oh.
things which are going to make us change our support vector. And because they're making us change our support vectors, they're changing the weights.
Oh, so there's like 3 parts to it. Oh.
Yes, there is. We've got good classification. This is a positive point. That's perfect out here. We don't care. It does not change our classifier. This is a positive point that's inside the margin. And so we're going to have to adjust our margins because it's showing us this is a new support vector. Okay, so we're going to make a minor adjustment to our weights.
Okay.
And these are bad misclassifications, and they're going to live, way out here. Okay.
Mhm.
High amounts of misclassification, large amounts of loss.
Okay. Thank you so much.
Is anybody else? I can give another 3-4 minutes. No? All right. So thank you, Yana, because I think that your questions are going to be very useful to people who are going to be watching this on the video. So
Thank you for the detailed explanation.
my pleasure. All right, have fun. See y'all later.